Okay, so we are discussing in the last class regarding how to convert a given regular expression to a non-deterministic finite automata. And I have asked you to solve one problem, that is create a non-deterministic finite automata for the regular expression, that is a plus b, a or b star. Okay, it is a or b star. Okay, so how we will proceed? Okay, so as I have already told you, we have to create first the smaller automatas for the smaller regular expression a and b first. So for a, what will be my automata? How the automata will look like? It will look like somewhat like this. So I am in state 1, I take the input symbol a and I reach the final state 2. Okay, similarly for b, what will happen? Suppose I am in state 3, I take the input symbol b and I reach the final state for the automata, that is 4. Okay, now how I will represent a or b? Okay, so to represent that in terms of a NDFA, I have to create a new state, that is state suppose 5. I can make an empty transition to either to 1 or to 3 from state 5. Okay, and then I can process the input symbol a and b respectively. Okay, and from 2 and 4 I can again make empty transition to reach a final state 6. Okay, so this will be my NDFA for A or B. Okay, now I have to apply the clean closure operator. Okay, so to do that I have to remove it as a final state. So 6 will no longer become the final state. Okay, and I can have, so let me tell you what can happen. So from 6 I can move to a state. So this star implies what? 0 or more occurrences of A or B. Okay, so I create a new state 7 where there is through an empty transition, and from 7 I can again make an empty transition and go to final state 8. Now this 7 I have created to with to directly come to so I created a starting state, suppose 9. Okay, so 9 will be my starting state. From there with empty transition I go to 7, and from there with another empty transition I go to the final state 8. So from 9 to 7 to 8 represents a the automata which accepts no string. Okay, so a plus b star is what? It can be empty, it can be a, it can be b. Okay, it can be a b. Okay, it can be a, like this. So to represent the first empty symbol, what I have done is I created the starting state as 9. Through an empty transition I go to 7, and from 7 I again go to the final state 8. Okay, now how to do it recursively? So from this 7 I can enter this loop through an empty transition. Understand? So if I have to accept a, I first have to go from 9 to 7, then 7 to 5, and then 5 to 1, and then I will consume the symbol a, will reach 2, and then will make an empty transition to reach 6 first, and from 6 again I will reach at 7, and from 7 I will reach at the final state 8. Understand? Suppose I have to consume b, then I will have to take this path. So from 7 I have to go to 5, then 5 to 3, 3 from 3 I will consume the symbol b, then go to 4, 4 to 6, again 6 to 7, and will reach the final state 8. Okay, so this way we create non-deterministic finite automata for regular expression having this clean closure operator. Okay. So okay. So now let us start the third step of the lexical analysis. Okay. That is converting a non-deterministic finite automata to a deterministic finite automata. Conversion of NDFA to a DFA. So how a NDFA different from a DFA? As I have already told you, the first is multiple transition, which means from a given state, when we are consuming a given input symbol, we can have more than one transition. And second is what we call as empty transitions. Okay. So while converting a NDFA to DFA, I have to take care of these two things. Okay. So empty transition means what? Empty transition means from a given state without consuming any symbol, I can make a transition. Okay, that is an empty transition. So multiple transitions are taken care by what we call as subset construction method. Okay, what does this mean? This means the if more than one states are reaching uh, are reachable from a given state for a given input symbol, then we can combine those set of states and we can create a new state. Okay, understood? For example, suppose the given NFA is like this. From state 1 with a input symbol A, I can either stay in state 1 or I can go to state 2. Okay, and in state 2 I can on input symbol B, I will remain in state 2, and state 2 is my final state. So what I can do is here, so this is my starting state. Okay, I can represent that on consuming input symbol A, I can go to a say I can go to a state A, which is nothing but this is equal to set of states 1 and 2 in NFA. So in DFA, this we create a new state capital A, which represents the set of states 1 and 2. Okay, and in A, on consuming symbol A, I will remain there. Okay, and on B, okay, on B, I will go to state 2. Okay, understood? So now since the final state 2 is there in A, I have to make this A as also a final state in DFA. Understood? So this way we convert we remove the multiple transitions of an NFA. So another is called empty transitions. How we'll take care of empty transitions? So I'll start a new page. It's called empty transition handling. Okay, so I need to give you one definition for handling empty transition, that is called epsilon closure. Epsilon closure is the set of states reachable from a given state through empty transitions. Okay, So so suppose my NFA is like this. I go to state 3, which is the final state. Then what will be my epsilon closure of epsilon closure of 1? So epsilon closure of 1 is without consuming any symbol, how many, which are the set of states I am reaching. Okay, so I can always remain in 1. Okay, so epsilon closure of 1 will always contain 1. Then there is an empty transition from 1 to 2. So epsilon closure of 1 will also contain 2. And from 2 again I can make another empty transition to reach at 3. So epsilon closure of 1 will be what? 1, 2 and 3. So these are the states I can reach only through empty transitions without consuming any symbol. Okay. So to remove empty transitions for a DFA, what we need to do is we need to create unique state that represents the epsilon closure of a state. That means epsilon closure of 1 is what? The 1, 2, 3, and that I represent as capital A. Okay. Similarly, what will be my epsilon closure of 2? It will be 2 or 3. And this state I'll represent it uniquely as a state B. Okay. So what can happen? So I'll start with state, suppose. So in DFA I'll start with epsilon closure of the starting state. So that is A. Okay. From A, what I can achieve? So from A, if I do an uh, transition for input symbol A, then what can happen? So either so what can happen? So in state 1, if I encounter an input symbol A, then I can go to state 2, I can consume A and remain there. Okay, so let me write it down. So transition function of A with respect to A will be what? So first I can make an empty transition to 2, consume A and remain there. So 2 will be one state, and again I can make further an empty transition to reach 3. So 3 can also be a reachable state on consuming A. So delta of A is 2, 3, and 2, 3 is what? Is the state B. So I can write that with A, I go to state B. Understood? Now on B, with A, what can happen? So B is what? 2, 3. So on 2, 3, if I consume A, then I can either remain in 2, or I can, after consuming the symbol A, I can go to state 3. So it will be B itself. Understood? And on consuming B, what can happen? So if I consume B, then what can happen? Then I can make an empty transition to 3 first and then consume the symbol B. Okay, so delta of B with B is 3. Okay, so this is the DFA for the given NFA. Okay, let us now try to solve on solve a bit larger problem. Okay, and that will be more clear to you how things are. So let us start. Let me first draw the diagram. So I am in state 1. Okay, I go to state 5 through an empty transition. This way I make an empty transition and reach the state 3. From state 3 to transition I reach the state 4. Okay, from 1 I make an empty transition and reach the state 2. From state 2 I go back and state A. Okay, from 5 on hitting the symbol A I go to the final state 6. So I have two final states, 6 and 4. Okay, now I need to create a DFA for it. How will you do that? So as I have already told you, first you have to find out what is the epsilon closure of the starting state. So epsilon closure of 1 is what? It can be 2, it can be 3, it can be 5 and 1 itself. So it will be 1, 2, 3 and 5. Okay, and this I represent it as state A. So this is my starting state. Okay, now with A in hand, and I suppose I want to see what will be the effect if I consume symbol A. So from 5, so from any of these states which are present in A, I need to see what is the transition. So from 2 I have, for a given after consuming symbol A I can reach 3, and from 5 after consuming symbol I can reach 6, state 6. So I can say that delta of A comma A will be, what is the state? So it can either be 3 or 6. Understood? And this I represent it as capital B because it is a unique set of states. Okay. Now from A, if I get a B, what can happen? From A, if I get a B, then in any of this state, if there is a transition corresponding to B, so from state 3, which is present in capital A, I have a transition for input symbol B, and it is reaching the state 4. So I can say that A on consuming the input symbol B will reach the state 4, which will be the final state. Okay. Then from B, if I consume, so B is also 3 and 6 and it contains the state 3. So B also can consume the input symbol B and reach at 4. Okay. And B can consume A and remain at state 6. Okay. So this will be the DFA for the given NDFA. Okay, so this way you have to consider, you have to break the multiple transitions by creating a set of states which is unique and represent it as a new state in the DFA, and you have to consider the epsilon closure to remove the empty transitions. Okay, so let me give you an exercise to do for you to do. So let me draw it in a bigger problem. So suppose this is state 0, go to state 1, 1, 2, I have 2, 2, 2, 3, 3, 2, here I can go to 4, 4, 2, 5, and both 3 and 5 can meet at 6. From 6 I can have 7, sorry, 7, 7 to 8, and 8 to 9. So it's a pretty large NFA we have considered, and from 0 I can directly reach here to 7, and from 6 I can go back to 1. Okay, so here is the empty transition. With epsilon I can go here with a, then epsilon, epsilon, then I can have again another epsilon. I can consume a again and b again, and this is an epsilon and this is an epsilon. So my question will be, first question, what will be the equivalent regular expression for this NFA? Okay, and the second question is, construct a DFA from this NFA. Okay, stop.